value to the address stored in that place on the stack. Okay, and then the caller. So now the call instruction has been reversed. Now the caller will pop off the arguments, and now the call is complete. So everything that you put on the stack now came off, and this is how the call really works. Okay, call and return. Yeah.
You mentioned the frame pointer would be pointing to a location after the same frame pointer location. Like, let's say if I call a new routine,
Yeah.
the frame pointer would point to.
So when this function call is made, right, the frame pointer is there, and after control comes into the callee, right, that is when the callee resets the frame pointer to point to its frame.
What about the actual arguments that will be passed to the routine? They would be stored above the frame pointer.
So they are here, right?
Okay.
They are here. So this is the order, right? So the save frame pointer, return address, argument 1, and argument 2. Okay? Now the second, let me come back to the question because so the significance of the frame pointer is that everything here is accessed using a constant offset from the frame pointer. So the frame pointer itself will point to the same frame pointer plus 1 will correspond to the return address, plus 1 will correspond to argument 1, and so on. Right? Or plus 4 if we are talking about a third with the subclass. Yeah, go on.
If they are allowed to access in both directions, are they using decrement operator and increment operator of the frame pointer? Like it's, for example, if I want to access an action parameter, I'll have to move few locations above the frame pointer.
Yeah, the instruction set basically allows you to say, get me the value that is 8 bytes above the frame pointer.
Is it not possible that I could infringe into data that is?
Yeah, you can do anything. That's machine, right? It's assembly code. You can do whatever you want.
Wouldn't that like corrupt the data of a previously stored?
You're supposed to know what you're doing, right? You're programming in assembly. Yeah.
Maybe I'm thinking
Yeah.
of a different architecture, but aren't there argument registers that this data is saved in anyway?
So there are different conventions for passing parameters. Okay, on the 32-bit Intel architecture, right? So these conventions are so the stack and parameter passing conventions. Right, so these conventions differ across operating systems and architectures, right? So what we are talking about here, you can say again for specificity, we will stick to the particular combination of Linux and Intel 32-bit architecture. Okay, so it's not that these conventions are widely different across different processors and so on. So there are a few possibilities, and you just simply cycle through those. But we don't. It will be inconvenient to just say on this processor, this operating system, something, right? So we'll just stick to one. Okay. So coming back to your question, there are operating systems and architectures where the convention is that you put the parameters in a register, right? So for instance, it may say your A register contains this, and B register contains the second parameter, and things like that. Okay. So on RISC architectures, right, reduced instruction set architectures, ARM, for instance, the more common thing to do is to pass arguments using registers. On 64-bit Intel, there are two conventions. One is you put the arguments, the first some number of arguments in registers and the rest on the stack. Okay. On 32-bit, the convention is that everything goes on the stack. And if you're going to write exploits, it's much more convenient when everything is on the stack. Okay. So that's why we are going to worry about that
What is
configuration.
the actual data type of the frame pointer, like what does it store?
The frame pointer is a pointer, right? So it contains an address.
Integer value or what?
It's an address, right? So again, this assembly, right? Don't think too much about types and stuff, right? Everything is bits, right? So it's the responsibility of the compiler for your high-level language to translate whatever type data you have into something that makes sense at the assembly level. Any other questions? Okay, so that's gives us. You can say no, right? So it's fine. Let's. So that shows you how a buffer overflow or a stack smashing attack works, right? So you have, so here's a function, right, f. Right? F takes two arguments. The first one is a pointer to an integer, right? So in C, integer pointers and arrays are roughly the same thing. So you might pass in an integer pointer and then access it using an index as if it's an array. Okay, so because an array is represented by its base address in C. So it has two parameters, and then it has a local variable, which is an array, and then it has another local variable, I. Okay? So based on what we discussed so far, when you are in here, this is how the stack is going to look like. So you have the arguments, this argument is over there, second argument is over here, then there's return address, then that's the saved base pointer, and then array buff is allocated here. And again, remember, because the addresses increase this way, buff 0 will be here and buff 99 will be there. Okay? And then I might be allocated in that place. Okay? So now what happens here, if you look through the program, is that this function takes two parameters. A is an array, and the n is the number of elements of the, or the length of the array, right? And so what it does is it basically copies the value from A to buff before anything happens. Okay? But the error is that the buff has capacity only for 100 elements, and this has size of n, and if n happens to be larger than 100, then you will overflow and then write into the return address. Okay? So a typical vulnerability is this kind of a buffer overflow where the program contains a vulnerability where it doesn't check the size of a buffer and ends up copying more data, and now ends up overriding some data, something else in memory that resides past the end of this data. Okay, so let's see how that. So maybe I should. Apparently I don't, but that's okay. So what happens is that when you end up overriding this, you overwrite the return address, right? And therefore what's going to happen is that when this function f returns, it's going to jump to whatever address is stored here. But since this has been overwritten, right? And now if you think that the data A came from an attacker, that means that the attacker controls the content of the return address, right? Which means that the attacker controls where the execution is going to continue, right? So this is how the attacker carries out what is called a control flow hijack, right? So the control flow of the program has been altered in a way that the attacker wishes, and so we call it hijack. Yeah.
Can this also cause memory leak somehow?
Memory leak. Okay, so it's nothing. This has nothing to do with memory leak. Right? This is, in general, this is called memory corruption because if you think about the high-level program, right, the result of writing beyond the end of a buffer is undefined in C language, right, which is a way of saying that it is an invalid operation and a valid program should never do it. Okay? So when something that's not permitted actually happens in relation to objects in memory, then we call that as a memory corruption. Okay? Was there another question?
So
Yeah.
So the compiler will stop it, right?
Why would the compiler stop it?
Because if we try to run this, I think we'll get a segmentation
Oh,
problem.
so you should read more C, right? The C compilers don't stop you from. So again, think about how C came about, right? Because the term that's commonly used is it's high-level assembly, right? So that was the purpose of how C was designed, right? So it was designed so that you could implement things like operating systems, that that you could control how memory layout works, and so essentially you could control things at a very fine granularity as if you're writing code in assembly, right? And so consistent with that philosophy is that the programmer knows, and then if they are doing something that you think it should be permitted, well, let the programmer decide. Yeah.
For that, the attacker will have to store his program in a memory location.
Yeah, so I'll get to that. Yeah, is there any, yeah.
I was going to say something related to that. So basically, the address given to be stored at buff 101. Once the callee returns, it would go to that function instead of.
Correct. Whatever A contained at position, let's say 101, right? That would be what will override the return address. So whatever the attacker puts at location 101 of this array A would be the place where this function will return, right? And what the attacker does is the attacker puts the return address to point to the beginning of the buffer. Okay? Why? Because the attacker already controls all of this, right? Because the program copies all the data from A into buff, right? So what the attacker can do is they can put their code in A, right? Let's say in A0 through A99, they can put their code, and then A101 contains a pointer back to the beginning of the buffer. So in order for all of this to work, the attacker has to know exactly, where is this, right? What is this? Is this location, 1000 or 1700 or, 0x, B00, whatever, right? So whatever is the address, they have to know exactly. Therefore, so that they can point the return address to go to the beginning of that. Okay. So this is how the simplest form of stack smashing attack works. Okay. So you can do this, and you can get, the attacker can get their code to run. Okay, so this type of attack attack, right? So how many of you have heard of internet worm? Okay, so tell me, when did this happen? So it happened in the, I believe it was 1988. Okay, so it's an undergraduate in Cornell decided that they'll have, they will try to launch a worm on what was called ARPANET at that time, right? So the internet in the current form didn't really exist, but ARPANET was essentially the same thing. And the only difference being that not everybody had access, only a bunch of universities and labs had access to this network. And so this kind of stack smashing attack was popularized in that attack. Okay. And when the internet became public, then the threat of stack smashing became significant enough, so people had to come up with ways to prevent stack smashing. Okay, so the very first solution. So I told you that one of the things I want you to do from this course is one of the things I want you to learn from this course is to think like an attacker, right? So what we are going to do is we are going to talk about an attack, a mitigation technique, how the attacker goes around the mitigation technique, and how this continues for what seems like ever. Okay, so I'm going to let's try to do it using that one board. So the first popular solution is called canaries. So you might have heard of canary in a coal mine, right? So it's something that is, you think of it as something that you sacrifice in a sense, right? Something that gets and by checking if this bird died in a mine, you will know whether there are poisonous fumes, right? So in the case of stack smashing, the entity you want to protect is the return address, right? And you want to see whether you want to put in a canary that will tell you whether the return address was corrupted. So what you do is you leave the return address over here, and then right. So what you do is you simply insert a canary value here, and typically the canary will be a random value. Okay, and what happens in this case is that the caller, as soon as the caller takes over, instead of pushing the saved BP first, it first stores, it pushes a canary value there, right? And now the idea is that if the attacker performs a buffer overflow, if the canary is here, then the canary will also be corrupted while the attempt to override the return address. Okay? And the reason why it's a random value is because you don't want the attacker to be able to corrupt the canary without you being able to detect it. Right? So if it's a random value, then the attacker wouldn't know what the random value is, and therefore if the attacker simply overrode that canary, then you will know, okay, it's been overridden, right? So what the callee has to do is, before it returns, the callee has to check whether the canary is intact or not. Okay, so if the canary is not intact, it doesn't have the original value that was written at the beginning of the function, then you're going to say this canary has been overwritten, and basically the program will abort. Right? So the typical response when this is detected is to abort the program. Okay. Yeah.
So this is under the assumption that for this particular code snippet that you have given, this kind of works because we are going through all the buffers.
Yeah.
But say for example, instead of incrementing it by 1, it is incremented by 2. And so it's possible that you can miss the canary and hit the return address.
Correct. You're right. So none of these are, foolproof. So it's so what you hope for is the solution you design is something that works in most cases, right? Or rather, in the typical program works, right? So again, this only protects against a buffer overflow, right? So you could also have what is called a buffer underflow, right? Which is you basically write from start from here and then you keep going down, right? And if you did that, and if you overflowed, then you will write here, right? And if you did that, there is no protection, right? Same way, because it's assumed that mostly you will write in the buffers from the beginning to the end. So mostly it will be overflow and not an underflow. So there are many assumptions you make in order to get this to work. Okay, so the canary is sort of the first solution. And of course, once the canary is in place, then the attackers are going to try to figure out, okay, is there something I can do that will allow me to get around this? Okay? So, so what are the things that the attacker can do, right? There are, if you cannot, so there is a canary here, so the attacker has to either avoid crossing the canary or find a way to cross the canary without overriding the canary, right? So the first thing that the attacker can do is to sort of jump across the canary,